7.6 Day 2, we're looking at linear programming, but now we're going to solve real-life problems. So example 5 shows how linear programming can help find the maximum profit in a business application. A candy manufacturer wants to maximize the combined profit for two types of boxed chocolates. A box of chocolate-covered cream yields a profit of $1.50 per box, and a box of chocolate-covered nuts yields a profit of $2 per box. Market tests and available resources indicate the following constraints. The combined production level must not exceed 1,200 boxes per month. The demand for chocolate-covered nuts is no more than half the demand for chocolate-covered creams. The production level for chocolate-covered creams must be less than or equal to 600 boxes, plus 3 times the production level for chocolate-covered nuts. Then we need to find what is the maximum monthly profit, and then how many boxes of each type are produced per month to yield the maximum profit. So maximum monthly profit, and then how many boxes of each type are produced to yield that maximum profit. So first we need to identify our variables. And so we are going to say, so how many boxes of each type. So that kind of helps us out with what we need to write. So how many boxes? So we're going to have two types of boxes. There's X, which is our, I'm going to say, chocolate-covered creams. And then Y equals the chocolate-covered nuts. Then we're talking about profit. So the profit, it yields a profit of $1.50 per box and $2 per box. So that's our objective function. P equals 1.5x plus 2y. So that's the objective function that we'll use later on. So now we need to describe our constraints, or write our constraints. So it says the combined production level must not exceed 1,200 boxes per month. So x plus y has to be less than or equal to 1,200 boxes. Then it says the demand for chocolate-covered nuts, so y, is no more than half the demand for chocolate-covered cream. So that's less than or equal to 1/2 x. Then we will rewrite that a little bit later. The production level for chocolate-covered creams must be less than or equal to 600 boxes plus 3 times the production level for chocolate-covered nuts. So chocolate-covered creams, so X must be less than or equal to 600 boxes plus 3 times the production level for the chocolate-covered nuts, Y. And then we have to, of course, say that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. So here are the constraints. And then, of course, our profit, our objective function. So those are the things you need to write. So notice that maximum monthly profit, that helps us with our objective function. So what is, and so it's, sometimes the hard part about this is identifying, well, what is the objective function that I write? And then, what are the variables? So maybe this can kind of help you out. So now once we do that, we need to graph like we did the day before or the previous lesson, and then find the vertices and then plug it in, and we're looking for maximum monthly profit. So what we need to do is let's try to rewrite this equation here. So I'm going to multiply by 2 first. So this is 2y less than or equal to x, or this is negative x plus 2y is less than or equal to 0. Let's do the same thing for this function here. So let's subtract 3y. So this is x minus 3y is less than or equal to 600. Okay, and then we could rewrite this in slope-intercept form if we would like, but let's kind of leave it where it is for now. So I want a graph. So I went ahead and labeled the x and y axis by going by 200s to help us out. So this first one is x plus y is less than or equal to 1,200. So that tells me that my x and y intercepts are at 1,200. So I can start there, and it's going to be less than that value. Then we can go ahead and graph the next equation. So this pink one right here. So we have 2y is less than or equal to x, or negative x plus 2y is less than or equal to 0. And, we can even think about this in this form already. Y is less than or equal to 1/2 x. So I know that it starts here. And then I know it's scaled, but basically I go up 1, right 2. So if I go up 200, then right 400, up to right 400. That kind of helps me out with that graph. And again, it's less than, so I know I'm going to shade in this region here. Then we have one more equation. It's this one right here. So x minus 3y is less than or equal to 600. So let me find my x-intercept. So y is 0. When y is 0, x is 600. So that's a good starting point. And then, so what we probably want to do is solve the system. And so let's solve the system between this line here and then the purple one that I have. So this one here. Let's do that to see if we can find the intercept here. So I'm going to multiply this equation by -1, so I cancel out the x's. So negative x plus 3y equals 600. Then I'm going to add the x plus y equals 1200. And I apologize, that should be negative 600 there. Then this should be 4y equals 600 divided by 4. So y equals, so 150. So y equals 150 here. And then if we plug it back in, so we have x plus 150 equals 1200. Subtract 50 from both sides. We find that x equals 1050. So that is where it intersects. Approximately right here, somewhere around here. So here is the line. More importantly, our vertice here is 1050. And then 150. Then we know this is at, x is 800, y is 400. And then we're shading below, and then for the green line here, we know that we are shading above, because when we solve for it, we have to flip the inequality, right? X minus 3y less than or equal to 600. Negative 3y is less than or equal to negative x plus 600. Then you divide by a negative. So we're actually seeing that it's greater than that line here. So therefore, we shade in this region here. So that's our solution region. Now we're looking at maximum. What's the maximum? So here are our vertices, 1, 2, 3, 4. So this is at x is 600, y is 0. So we can go ahead and talk about our vertices or label our vertices. So our vertices are at 0, 0, 800, 400. Then we have 1050, 150. And then we have 600, 0. So let's plug that into our objective function at the top. So p equals 1.5x plus 2y. And so we get 1.5 times 0 plus 2 times 0. Obviously, that's going to be 0. Then we'll plug in the rest. 1.5 times 800 plus 2 times 400. And then I'm just going to plug them all in first before I solve for it. 2 times 150. And 1.5 times 600 plus 2 times 0. And then 1.5 times, I think that's it actually, 4 of them. Okay, so this is obviously 0. And then here 1.5 times 800 plus 2 times 400 is 2,000. And then we have 1,050 and 150. That's going to be 1,875. Then 1.5 times 600, that's going to be 900. So we're looking for maximum profit or optimal profit. And we find that our optimal profit is $2,000. Oops. $2,000 when, let's see, 800 chocolate covered cream boxes and 400 chocolate covered nut boxes are produced. All right. So what's nice about the next problem, it's pretty fast. In example 5, the candy manufacturer improves the production of chocolate-covered cream so that the profit is $2.50 per box. The constraints do not change, so we want to know what is a maximum monthly profit? How many boxes of each type are produced per month to yield the maximum profit? So the only thing that's changing, I hope you see, is our objective function. So change that objective function, knowing that the profit is now $2.50 per chocolate-covered cream box, and then now find the maximum profit and how many boxes of each type. Okay, so trying this out, your new objective function is p equals 2.5x plus 2y, and we use the same exact vertices, so when you plug it in, you find that the max profit is $2,925 when 1,050 chocolate-covered cream and 150 chocolate-covered nuts are produced.